Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 18 on intermolecular forces, which are simply the forces between molecules. And so when we were putting drops of water on this penny, we were able to get 43 drops on there because there are high intermolecular forces between the water molecules. And so intermolecular forces are important because they give us the properties of solids and liquids and gases. And so some of the properties would be the boiling or melting point, surface tension, capillary action, vapor pressure, and miscibility. And we'll talk about each of these. And in gases, there's not too many intermolecular forces because they're moving around really, really quickly. But when there are intermolecular forces, they explain the difference between an ideal gas, which can be explained using the ideal gas law, and real gases. And this usually occurs towards condensation. We can use a PV relationship to find it. And then finally, intermolecular forces are incredibly important in biology. In both enzymes and proteins, these forces between molecules are incredibly important. So let's make sure you know the difference between inter and intramolecular. Intermolecular are going to be the forces between molecules, so between this one and this one. Intramolecular are going to be within the molecule itself, and so we'll get to those when we start talking about covalent, ionic, and metallic bonding. But intermolecular forces are simply the forces between these molecules. And so let's take a look at them. Let's say we vary the strength. Let's say we make those forces weaker. What happens? They'll spread apart. What happens if we make them greater? They're going to come together. What happens if we make them even greater? They're going to come together and form a real nice structure, so something like a solid. And so what are some properties that are affected by intermolecular forces? Well, let's start with the melting point or the boiling point. And so melting point is when you go from a solid to a liquid. And so if there are greater forces, it's hard to get liquids to start to form. And boiling point is going to be these molecules actually jumping off into a gas. And so the greater those intermolecular forces are, the harder for it is to move off. Surface tension is going to be like a skin over a liquid. And so imagine down here that we're looking down at 3 drops of 3 different liquids. And those liquids are mercury, alcohol, and water. Could you match them appropriately? Well, mercury is going to have the greatest intermolecular forces, so those are going to be right here. And water is going to be next, and so it's going to form this nice bubble due to hydrogen bonding, and then alcohol is going to spread out. And so we can look at intermolecular forces. It's going to tell us how much of that skin on the surface is going to form. Capillary action is going to be movement of a liquid up a tube. And so if we're looking at water, not only is water attracted to itself, we call that cohesion, but it's also going to be attracted to the tube that it's in. We call that adhesion. And the thinner we make that tube, the more the water is going to move up. And that's how water gets up a tree. There are really tiny tubes called xylem that allow water to move up it. But if we were to look at something like mercury, it's attracted to itself, but it's not attracted to its surroundings. And so it's actually going to move down in a capillary tube. Next is vapor pressure, and vapor pressure is measured in a closed system. So if we put a liquid in a closed system, it's going to be the amount of pressure exerted by the gases. And so how are we going to get more gases there? They're going to jump from liquid to a gas stage. And so the higher that vapor pressure is, the more volatile that liquid is going to be. So alcohol, for example, is going to have high volatility, and that's because a lot of it is jumping out of this liquid phase into the gas phase because there are low intermolecular forces. Miscibility, you can think of that as like mixability. How easy is it for 2 different materials to mix together? Well, you know that water and gasoline don't mix well. The reason why is that water is going to be polar and this gasoline is not. But water does mix readily with hydrochloric acid, and that's because the hydrochloric acid molecule is going to be polar. And so these like charges are able to dissolve like charges, and vice versa. Also, this explains why water is really, really good at breaking down ionic compounds. And so this is salt, and salt is really high bonds in an ionic compound, but if you add water to it, it readily breaks apart. And the reason why is those chloride ions, or the chlorine ions, are going to have a negative charge, and the positive parts of the water are able to surround it. And if I add a sodium ion here, which is positive, the negative parts of the water are going to surround it, and that allows it to break down. When we get to gases, remember, we have ideal gases, which can be explained using the ideal gas law, where PV equals nRT. And then we have real gases. Now, an ideal gas is an imaginary model, and it assumes that there's no attraction between these molecules, and that there's an infinite amount of space for these molecules to move around. But as we start to cool down those gases towards a liquid phase, we start to get attraction, intermolecular attraction between these molecules. And also, we have a finite kind of a space, and so this law starts to fall apart. So if we were actually to graph it, PV over RT for an ideal gas, if we graph it, will always be 1. But if we were to vary the temperature for a real gas, let's try nitrogen, at 1,000 Kelvin it would look like that, 500 it would look like that, and 200 it would look like that. Now the farther you are off that blue line, the farther you are off of an ideal gas. And so you can see that as we cool nitrogen down, as we get it closer towards that condensation point, that model of an ideal gas is falling apart. We could look at different gases at 313 K as well. Let's look at hydrogen versus nitrogen. You can see hydrogen is going to be more like an ideal gas, and that has to do that it's a smaller mass and it's going to move more readily. It's also incredibly important, these intermolecular forces in biological systems, and so this is an enzyme. An enzyme is basically a catalyst that breaks down a molecule. In this case, this could be sucrose, which is sugar, and it's broken down by sucrase. These intermolecular forces are incredibly important. It almost has to fit in like a key inside a lock. And enzymes and almost everything in life that's important are made of proteins, and there are huge intermolecular forces within this giant macromolecule that hold it together and give it its characteristic space. And so did you learn the following 2 things? To explain observations regarding solubility of ionic compounds, remember something like water, since it's polar, can break apart those ions and kind of usher them away from the ionic compound. And then finally, can you explain terms like vapor pressure, viscosity in terms of strength and type of intermolecular forces? We went through this list, and it's all based on those attractions between the molecules, and I hope that was helpful.